Start recording. I'll do the other things later. Okay, so announcements. First off, I've decided to try something new, which is to do our exam late in the semester. So we're going to do it right before the fall break. So it will be not next. So our next exam will not be this week. It's not going to be next week. It'll be the week after that. It'll be on the 14th. It'll be in here, just like the first exam. There will be a question. Most likely the digits question or something very similar to it that basically will be redemption points. So basically you'll be able to, whatever you get that will replace the grade on that question that you did on the first exam. So there'll be a chance for you to make up points if you mess that up on the first exam. Also let's see. I will be giving a practice exam out. I still have to figure out what's going to be on it, but there's probably going to be some fake file reading on there where basically I say, read this file, the file called this, right? Go through the lines and maybe it's a file with a bunch of numbers and I tell you to add up all the numbers or something like that. But basically something similar to what we did in Turtle, except without having to animate the turtles maybe. Or maybe we do something similar to animating the turtle and just, we'll see. You know, it's not particularly, but this does seem to be focusing a lot on file reading and some on dictionaries. As far as your latest assignment, which is PIG, note that it doesn't have a due date yet. That's because I've spoken with the TAs and they're like, well, we still got students working on all this other stuff. So I'm like, okay, so I'll give a due date probably closer to the time around when the exam is due for that one. PIG is split up into like 7 sub-exercises, but it's not so much a lot of coding because you can copy-paste a lot of that code into each solution, right? And basically build up, or if you write functions, you can call those functions for each part of it. But I will talk about that in just a sec. So let me just talk about, let's see, that in just a second. Do I have a dice? Where did I do the dice? What was the dice program I did last time was called? Did I save it before I wiped everything? Letter grade, no. All right. Oh, yeah, dice over here. Okay, cool. So we did do that. Properties. Open with Geany, says default. Okay, so the game we are going to be simulating is a game called Pig. Don't know why it's called Pig. Pig game dice. I don't know why it does that every single time, but it's a fairly straightforward dice game. And let's see. So this homework was created by by Todd Neller, who basically has done way too much analysis on the game on the Pig dice game. In fact, his webpage, right? So if we go to his webpage, we can actually see all the stuff he's done on Pig. So there we go, Pig resources. Pedagogical, self-chain. No, that's not what I wanted. Game of Pig website, there we go. So he wrote a small program that back in the day, Java used to be how you run things, but these days not so much. Let's see. Used to be that there, so let's go ahead and install that. Sudo apt install open JDK 8-JDK. And I just want to show you this because it's a very well-designed thing. Oh. Yes. Please install. So that doesn't take too long to install, despite it saying it's going to take a bit to install. So the game of Pig, basically you have, it's a race to 100 points with two people. And it works pretty much as follows. and I'll play against the computer here. It's a bit small, unfortunately, but I think you can see basically that I've got my roll. Basically, I've got two choices. I can roll or I can hold. Okay? And it's got a computed win probability over here. I have a 53% chance of winning if I play optimally. There's a number of games that are solving games is very popular among computer scientists. And by solving games, I mean figuring out how do you win a game all the time. Some games are solved, like Connect 4, solved. Yep, so Connect 4, basically, so this is Connect 4 where basically you drop disks and try to call them out. And notice that it has a mathematical solution. Two-player game with perfect information, which means that everybody knows how basically how the game can play. There's no concealing anything from another player. And basically you can solve it with brute force, and you can always win if you play perfectly if you're the first player. So games like that, similar to tic-tac-toe, you can win if you play perfectly, but, well, you can at least always get a tie if you play perfectly. With Pig, though, because we're dealing with dice, there's probability involved. So it's pretty simple. Rolling the die, if I roll a 1, my turn's over. I lose all the points I accrued this turn. The computer's playing now. Notice he's rolling the dice. And once he rolls to get to a score that he wanted, he just held, like you do in blackjack. And he stored his points to 24. So he stored the 24 points he won that turn. First person to hit 100 wins. So again, if I roll, I've got 2. I could hold and get 2 points for the turn, or I can keep rolling. And see, I made it all the way up to 14 points, and then I hit a 1, and I lost my stuff. So he busted out this turn. Very quick bust on my turn, right? And it turns out busting it happens a whole lot in Pig. In fact, one of your exercises, I do ask you to compute the probability that you can go from 0 to 100 in a single turn. How do you do that? Simulate a whole bunch of games or a whole bunch of turns of this game, right? So there's going to be a lot of, right, doing something like a Monte Carlo simulation sounds like it's really complicated and really tough. But all I'm asking you to do is roll a die until you hit a certain number. Do it 1,000,000 times, and then asking you to count up the results, right? That's really all I'm asking you to do. So there, I've got a whole. The strategy I like. The strategy I use a lot, because it's a decent strategy, is hold at 20, which means that once I hit 20, that's when I'll hit the hold button. And the computations you do basically means that you're going to bust 32% of the time on that. You're going to 62% of the time you bust on that strategy. But it does a good job of getting the score up. So my score is 44 to his 63. Now the computer's rolling again. By the way, why is it called a pig? I don't know. But when you roll a 1, that's a pig. Okay, not too far away, but I'm still. Now, there is optimal strategies that you can use, basically. Based on the turn number, how close you are to 20. How close you are to this. How far ahead the computer is ahead of you. In fact, you can see basically there's this complicated graph. I have no idea what to do, but basically this is a visualization of the optimal things to do in a two-player game of Pig. So you're going to both make it a two-player game and a game where you play against the computer. Now there's I remember I saw a Facebook meme, so basically where of Scooby-Doo, and like, let's see who's really under the mask, and the mask was AI, and it pulls it up, and it's a bunch of if-else statements, and that's really all it is, especially on this one. So yes, you're making a very basic AI, but all it is a bunch of if-else statements, and not too many of them. So to deal with that, I figured today we're going to talk about we're going to do something basically pretty simple. We're going to continue in our discussion of dice. We could also do, or we can, as it relates to Dungeons and Dragons, basically because there's a lot of different dice there. We can generate a lot of numbers. We can simulate a lot of things statistically, like you're going to need to do in your program. Or we could let's see. Yeah, dice seems best actually, because if we had to do blackjack, that would just be a lot of stuff. But yeah, so let's go ahead and just continue what we were talking about from last time. So what we were doing last time was that I created a roll dice method. Now, we also introduced the concept of, which you do not have to use at any point. I'm not going to force you to use this, but the concept of default variables, where basically I say, hey, right, normally you take in an argument called num dice, but you could say, hey, if you don't provide me a number of dice that you want to roll, I'll just say it's by default 1, and number size is equal to 6. So by default, when I call roll dice, let's see. When I call roll dice, it will give me something randomly from it will give me something random from 1 to 6. In fact, this should be roll dice. If I call it without any arguments, it gives me 1d6. Okay. Now what we were, so here basically though, and remember I'm going to be talking in terms of I'm going to be using I guess nerd notation for dice, which is that I'm going to be talking about dice, well, in this format. This is the format I'll be talking about dice. So if I say 3d6, that means I'm going to be rolling 3 6-sided dice. 3d6 is just quicker to say than rolling 3 6-sided die. So 3 6-sided die. If I say I'm going to roll, another common one is 1d20, which is pretty simple. Roll 1 20-sided die. If I say 2d8 or 2d6, 2d8 means 2, right? So the first number is the number of dice. The second number is the type of die it is. So 2d8, 2 8-sided die. 2d6, 2 6-sided die. And what we're going to be simulating today, I guess, is basically the chance that a fighter can, we'll go ahead and basically we'll review what we did, and then we're going to start calculating the chance that basically a fighter might be able to kill a goblin in a single turn. So we'll see that. It's pretty simple statistics stuff. But again, we're going to just be using, Dungeons and Dragons to do that, because I know Dungeons and Dragons, and it's a dice game, and we're talking about dice games and probability. And, that's kind of just natural and easy to do. If you haven't played it, by the way, it's pretty fun. It's collaborative storytelling at its core, with some dice and the dice are just there most of the time to actually make noise rather than have anything happen. So, let's see. So we have this roll dice, which just simply rolls random numbers from one. Random gets you 1 to sides inclusive. So if I put in 6 here, this gives you 6. So all this does, right? Total is equal to 0. We're going to run this loop number of dice times. So if I say 2d6, this is going to roll 2 6-sided dice and give me the sum, right? So what we were doing last time is that we were computing the generated stats, right? Stats in Dungeons and Dragons go from, they range from a bottom score of 3 to a top score of 18 in character generation, right? Because the way you generate a stat is 46 drop the lowest, okay? Which meant you roll 6-sided die and you drop the lowest roll. And what this does is that it skews things, as we saw, much more in favor of getting having better stats for your players than not. We can compare that to just rolling 3d6, but anyway, how did we generate that? Well, what we did is that we kept all 4 of our rolls, rather than just rolling 46 and just trying to figure it out from there. What we did is that we created a list to hold all our rolls. We rolled 4 dice and added them, each of them, into the list. And then we added them up all 4 of the numbers up, but subtracted out the smallest one, right? We can also see what would happen if basically that if we go for an even higher powered, if we wanted our adventurers to be really high powered, which would be just to where we could do roll 5d6, drop lowest 2. Okay? And here I'll be making use, and that's basically, we do the same thing, except we roll 5 dice. Okay? Again, 5. So here we're trying to get a number, we're generating, so here we're saying what's going to happen to the statistics if we let the players, rather than rolling 4d6 and drop 1, what's going to happen to them if they roll 5d6 and drop the 2 lowest? Now, we can only subtract the small minimum rolls, only get you the smallest one. So, one way we can, so we're going to have to figure out how to do this a different way. Got 5 numbers here, but I want to drop the lowest 2. So we're going to use a method that we introduced last time, a very useful method. I think I introduced it. Did I introduce sorted last time? Yeah, sorted, which returns a sorted version of whatever you're dealing with. So if I sort those rolls, it's going to be sorted from smallest to greatest. By default, sorting something puts something in ascending order, no matter what that is. So to show you guys what I mean, to emphasize that fact, right, if I take this and I take hello, right, throw it into Word, is equal to hello. Let's go ahead and preferences up the font size on that. It's always hard to judge when I'm outside of class what the proper size for class should be. But it's not 18, it should be closer to 24. There we go. Word is equal to hello. If I say sorted word, if I try to sort a string, it gives me a list of all the characters in alphabetical order, right? From the first in the alphabet to the last in the alphabet, right? So smallest to greatest. But what if I want it from greatest to smallest? Then reverse it. That's one way. I mean, there's probably a more efficient way to do it, but you can just simply reverse what you get. But anyway, if we sort our rolls, that will give me from the smallest to biggest. So what we can do is that we can slice off those last 2. Sorry, slice off those first 2. Basically, and just simply. So here, this would give me all the rolls sorted. That turns. This is still a list. Then I can slice from index 2 up to the end, and then add that up using the sum function. Notice that it's just function calls inside function calls inside function calls. So now if I do 5d6 drop lowest 2, all I have to do is plop in that method, and our statistics have actually considerably improved, with basically the chances going, on average it was like a 13 or 12 earlier, and now you're edging towards having a 14 or 15. So this definitely gets much better stats for your players. All right, so let's see. So let's talk about one of the things you do in Dungeons and Dragons, right? There's which is basically you go in and you slay monsters. 5e SRD. Now monsters basically have, so very, very, very quick rundown. Let's go ahead. Okay, don't show that again. That's kind of cringy. Okay, monsters by CR. Let's see. Control F, goblin. There we go. Goblins, little things from mythology, annoying things. Basically, with in Dungeons and Dragons, you basically have your combat is a huge part of any adventure game, and there's basically 2 statistics we have to consider. One is something called armor class, or AC, which basically means I need to roll a number and beat this armor class in order to hit it. And then there's hit points, which is the amount of, well, amount of a beating it can take. So let's go ahead and start doing some basic statistics on can I hit something, basically checking if we can hit something. Now, rolls in Dungeons & Dragons are basic to see if you can hit something. Pretty much every single roll in Dungeons & Dragons to see if you can do something is roll 1d20 and add the appropriate modifiers. Okay? And I'll just simply, I'm just simply going to, why are you popping up like that? I don't want to follow you on Twitter. Yeah, the appropriate thing for anything is 1d20, add a bunch of modifiers. And because I don't want to go too deep of a dive and turn this into a class on Dungeons & Dragons, I want to keep it as a class on statistics, I'm just going to basically wing the numbers and tell you what I believe they should be, because I've played that game way too much. I had too much free time in high school. So let's go ahead and see. So first thing we need to see is so here's our statistics. I'm going to comment them out and use them later and use this later. But yeah, actually I'll just use a different function. Def calc hits. Okay, now so first off we got to figure out what we're rolling here. So what we're rolling here to check if we're hitting something is basically basically we need to see if we're rolling something and it's beating, well, specifically beating the armor class. Specifically, we want to see if our fighter can hit the goblin. Okay. Now fighters, typically they're going to have a strength of 16, which translates to a +3 modifier, which means that in total, blah 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 blah. The actual part we care about, again, is basically what they're going to roll. Fighters will typically roll to hit a 1d20 + 5. Okay? Make sense to everybody? They're going to roll 1d20 + 5 to hit. So what we're going to do is calculate how often do we hit something with an AC of 15. How often do we hit this little guy over there? And it will turn out to be something of a bell curve, I think. But let's see. Well, not really a bell curve. It's actually uniform, but it's a uniform distribution. But we'll see what our statistics are. So, all right. So really, we don't need a dictionary quite yet. Hits are equal to 0 for blank. So we got to simulate this a bunch of times in order to get the number of statistics. For blank, let's see, target AC is equal to 15. So for blank in range 10,000. Let's go ahead and do 10,000 rolls to start out with. We got to see basically we're going to calculate rolling a 20-sided die. So roll die, 1d20, that gives me a number between 1 and 20. And then add 5 to the total. So roll is equal to roll dice, 1 through 20, and add 5 to it. Next, I got to see if I hit. If roll is greater than or equal to 20, is greater than or equal to the target AC, basically, if you roll that 20-sided die, add 5 to it, and it's greater than what the monster's armor class is, then you hit it. So we'll say hits plus 0, plus equals 1. And then basically we want to print out the statistics, which is hits divided by 10,000. Very simple thing over there. Rather than calling main, I'll go back up to the method, by the way. But rather than calling main, I'm just going to call, what was it called? Calc hits. Target is not defined. It's target AC. Forgot AC, right? very common thing to do. So we're hitting it 54% of the time, right? We can get a bit more accuracy on that with adding another roll to it. Right, so 55% of the time we're hitting. So that's how often the fighter is hitting. So again, my question is how often a fighter going to be killing a goblin in one hit? Right, this is standard fantasy trope. Like Lord of the Rings, they do it all the time, right? So actually hitting the creature or the target is only one part of it. Then once you hit it, you have to roll for damage. So death, calc, kill goblins. All right, so we want to, how many simulations do we want to do? Let's do trials is equal to, let's do 100,000 trials. Just try this. We've got to hit a target AC of 15. Okay. And basically, we only roll for damage if we hit. Otherwise, we miss. So we are going to basically keep track of our results in a dictionary. Okay. So trial, I spelled that trails. Trials is equal to that. So, and I think this is really all I need. For blank in range trials, what am I going to do? So again, I'm going to basically roll the 20. I'm going to roll that 20-sided die to see if I. So there's a two-step process to doing this. I've got to roll the die to see if I hit. 1d20 plus 5. Okay, and then if I hit, which is if the roll is greater than or equal to the target AC, that was a hit. So then I can see how much damage I do. So how much damage does a fighter do? Depends on the edition, but the most recent edition of Dungeons & Dragons, that would be, let's go ahead and say he's using a greatsword, which means he's going to do 2d6 damage, plus his strength modifier, which will be 3. So, again, I'm kind of pulling these numbers from thin air, but they're, if you actually check them, if you play Dungeons & Dragons, they should be very familiar. So damage, so the amount of damage that'll do is equal to rolling 2d6 plus 3. All right, and so now we're going to see, and so now we can add that to our statistics. Else, we're going to say damage is equal to 0. Actually, there's no need to, we can do it more efficient and say damage is equal to 0 by default. And if we actually hit, we roll for damage. And now what we'll do is that we will store the damage in results. So, and what we're going to do with our dictionary is that we're going to count the number of times we do a certain amount of damage. Okay? We're going to count the certain amount of time we're going to do this damage. So if the damage is not in the results, if I've not had this damage roll yet, then this is the first time I've seen it. So results, and notice this is the same format I've been doing for basically all of last lecture. If it's not in results, results is equal to 1. Results is equal to damage 1. Else results damage is equal to damage results, the number of times I've seen it before, plus 1. And then that's all I need for that. And then I can return results. and then I can calculate, and then I'll go ahead and do it in main, and do what I need to in main now. So now in main, what I'll do is I'll say, okay, so we've got our results. Right, here's our results here. And you can find these, by the way, on the GitHub. I've been making sure to upload them all to the GitHub. So I was just pausing there so you could catch up. But anyway, so now we've got our results is equal to results. Or rather not results. Results is equal to calc kill goblin print results, which will only give us so much, right? Gives us the number of times we've got a 0, an 8, an 11, 5. Oh, that's really out of order because dictionaries don't care about your order. They are anarchy incarnate, right? So what we can do is, though, is say, for damage in results.keys, right, which are basically the roles we did. And furthermore, we can say sorted to make sure that we get it in a sorted order. We can, if we did this, we could just simply say print damage, and let's see what we would get. So here's our damage rolls. Now let's figure out how much they did, how often we did them. Print damage, comma. What was the other? All right, results. So there's the key. Now we get the respective value for the key. And here's the rolls. So notice that we swing and we miss a lot. It's the most common result. So let's go ahead and, let's see. How many rolls did we do? We did 100,000. So, but now let's break it down into percentages by dividing by 100,000 because we did 100,000 rolls. So we missed 44% of the time. And then we got, so it makes sense. If we're doing 2d6 and adding 3, okay, for our damage, that means that we've got 2 6-sided dice, which means the minimum result is 2, okay? And then you add 3 to the minimum result, so the minimum result will be 5, and the maximum result will be 15, so, because that's 12, the maximum roll in there, plus 3. Now, how in the world, now why is it that basically that you've kind of got, if you notice, you've got this bell curve as well. Basically, you get a 5 as often as you get a 15. But 10 is the most often result, and you get a 9 and 11 basically at the same time, and then an 8 and a 12. This is a bell curve, right? Where basically, right, if we were to graph it out, you've basically got this hill that peaks, that basically is centered on 10, and it slopes down until it gets very low around to the 5 and the 15. This is a distribution that basically happens pretty much everywhere when it comes to height, you know, and weight in populations. But it's a very standard statistical thing. And this is because you roll 2d6. The most common result is going to be that 7 result, which is basically because you have a bunch of ways to make 7, which is, you know, you can roll a 1 and a 6, a 2 and a 5, a 3 and a 4, or a 4 and a 3. You know, you have a lot of results. You have more ways to make that result. So now to answer our original question is, how often are we killing that goblin? So, well, what we need to do is add up all the times that the percentages. We have to add up all the times. Sorry, the percentages of all the times that our damage was 7 or greater, because the goblin only has 7 HP. So if we add up all the time, percent kills is equal to 0. So in this, print out the damages, and then say if damage is greater than or equal to 7, that's enough to kill the goblin. So we'll add that percentage to percent kills plus equals. We don't normally accumulate stuff greater than 0, that's a float, but and less than 1, but it's time for everything. So print. So if you're a fighter and you're going up a goblin, you're actually gonna, if you can actually kill up the goblin and you're using a greatsword, you can kill that goblin half the time in an arbitrary roll. And that includes, by the way, the possibility that you might miss. So pretty cool. So let's go ahead and take a look at something slightly less esoteric than Dungeons and Dragons, and a bit more relevant, and possibly a bit more relevant to you if you want to make some money. All right. So gambling is not a great way to make money. It is not. But that's what we're going to look at, because statistical analysis is a lot, and probability, again, comes out of gambling. Now, who knows the game in a casino where the house has the least advantage? Blackjack. Blackjack is the game where the casino has the least advantage, right? It's not that the games are rigged completely, but they have to be rigged in some way, shape, or form for a casino to make money. It can't be a completely even game, because if with an infinite number of games, you're going to break even. Okay? If the players and the casino have even chances of winning in any particular game, you're not going to make any money. So there has to be an advantage to the house in some way, shape, or form in a casino. Okay? And then we're assuming nobody's cheating here, right? So blackjack is the game, though, where the house has the least advantage, just simply because of the mechanics of the game. Okay? Now, for those of you who do not know blackjack, that's okay. I will describe the rules here, because we're going to be using a small subset of the rules. We're not going to be talking about doubling down or splitting, okay? We're going to just be dealing with regular things. It's a very popular game called 21, and the goal is basically to get to as close to 21 without going over. Okay? The person who gets, and if you're assuming you're just playing against the dealer, the goal is to beat the dealer. Okay? Beat the dealer's roll. Right? So you can beat the dealer in a couple ways. The first is you can just get a natural blackjack with your first 2 cards. Now, you might be going, wait. 10, the highest value card is a 10, right? Well, actually, Jack, King, and Queen have their own values, and so do an ace. You can also reach a final score higher than the dealer without exceeding 21, or you can let the dealer draw cards until they exceed 21. If you go over 21, you automatically lose. That's called a bust. You can see kind of how this might play into, how this might play into our, whatchamacallit, how it might play into Pig, right? You bust on rolling a 1 here. Here you bust when you roll, when you go over 21, okay? Typically what you do is that you're dealt 2 cards. We're not going to worry about face up or face down rules, because we're talking about statistics here, okay? Now, cards have different values here. The values of a card are, for every card that has a number on it, the value of the card's the number. So 2s are worth 2, 6s are worth 6, 7s are worth 7, and so on and so forth. If you've got a Jack, a King, or a Queen, those are worth 10 points. So face cards are worth 10. So that leaves out only the face cards. Sorry, only the aces, right? So what are aces worth? Anyone? 1 or 11, right? You can choose an ace to be worth 1 or 11. So ace, right? An ace and a soft 17 on a blackjack. So the dealer has different rules about what they're supposed to do at certain the dealer has certain strategies. based off of statistics to get the house an edge. And again, you have to beat the dealer, which gives him an edge. You can't tie the dealer. You have to beat him. Right? But notice that there's like there's this table here of what to do. Right? If you've got an 18 to a 21 and the dealer's face-up card is this, then you do this. Right? Always stand there. So, or not stand there. What is S? Split. S. So stand. Yeah, hit. Stand, hit, and then notice there's DH, which is double, or stubble if you can't, then stand, and then split on these, or surrender, right? There's different things you can do in blackjack, but we're just going to consider two strategies. On your turn, you have two strategies. You can either hit or you can stand. Hit means you ask for an additional card, and if you go over 21, you bust and lose. Or you hold and hope your total is higher than the dealer's. Okay, so you can. So yeah, let's see. Aces are worth 11 points or 1 point, depending on how the games work out. So let's go ahead and program them in. So what we're going to do is that we are going to make use of lists a whole lot here, but we're going to start simulating some blackjack. So let's call this file blackjack.py. Blackjack sim, sim.py. Okay, because we're going to be simulating blackjack. First, let's go ahead and create a deck. Let's create a method that will create a deck. Def preferences, edit preferences, editor, interface, 1, 2, 3, 4. So first thing we have to do is create a deck using and this will give us some review of some nice not split operations, but operations we can do with lists, right? For instance, in Python, you can do a lot of cool things with lists. Let's go ahead and remember them. So one of the things we can do with lists is that you can add two lists together. List 1 plus list 1 is equal to 1 and 1. So that will concatenate two lists together. That's useful. Okay. Next thing we can do is we can also multiply a bunch of lists. So here, 1 times 4 plus 1 gives me 5 ones, right? Just like you can how you can replicate a string, you can replicate a list. So that's going to be pretty useful. Okay. So let's also show you something else useful, right? I can just totally create a list in a loop. For blank value in range, and I want to go let's go from 2 to, right, the lowest value card is a 2, the highest value card is an ace, which would be 11. So I can do something like this, print value. Notice how I put the value in a list like that. If I press F5 now, oh, it doesn't do anything because I forgot to call it, which is something I always forget to do in Python. Every single time. Because I totally know this stuff. And notice that basically it's printing out the list that holds 2, the list that holds 3, the list that holds 4, and the list that holds 5. Suits don't matter in blackjack. So all I care about, so I don't have to do anything funky there. So create deck. So there, what we can do is say, so what we can do is actually fairly straightforward. We can say deck is equal to an empty list. And then for each of the card values, right, we need 4 2s. So we can say deck is equal to deck plus the value times 4. And then deck is equal to create deck. Now, I'm not done yet because you'll see in a second. Oh, none. Got to return the deck. So here I've got 4 2s, 4 3s, 4 4s, 4 5s, 6s, 7s, 8s, 9s, 10s, and 11s. But we don't have the jacks, kings, and queens in there. The 11s are the aces, by the way. Right? So what we can do over here is go up to 11 here, right? And then leave out the aces, and then say for blank in range we have 3 face cards over here. Deck is equal to deck plus 10 times 4, right? So we've got 4 10s, right? Or we could just simply simplify this, and there's no need for a for loop, right? Deck is equal to what we have plus 12 of them, because there's 4 jacks, 4 kings, and 4 queens. And then you can add in our 4 aces as well. Oof. So there, we've got 2s, 3s, 4s, so, and we can check the size of the deck as well. Print deck, print len deck, and make sure we've got 52 cards to play with. Okay. So we've got 52 cards. Now, mind you, there's a slight issue here, which is that we need to actually shuffle the deck for when we're going to do simulations with it, right? So Python, shuffle, list. How do we do that in Python? Random.shuffle. Turns out that random, okay, so random, Python 3, turns out that random number generator is really useful. So because if I look, shuffle sequence X in place, and it will basically shuffle it for me. So I just throw random.shuffle the list, and it will shuffle it for me. So let's go ahead and import random. So I've got my deck, and then all I have to do to shuffle it is I just say random.shuffle. Makes sense that shuffling a deck, which is a random process, ends up in random. Random shuffle deck. It does it in place, so it doesn't return a new deck. And there, it shuffled it for me. Notice there's a lot of 10s there, because you have a lot of 10s because you've got 4 10. You've got a total of 16 cards that are worth 10 points. All right. The next thing is that we are going to represent a hand also as a list. And we can get the value of the hand kind of by summing it up. Right? It's fairly easy to sum up. So first off, def value of a hand, right? This will give us the value of a hand in blackjack, right? And we're going to assume that the hand is a list. Right? And typically you might just be tempted to do return sum of hand. But that's not necessarily what we want to do, right? Because remember, if I were to get an ace and a king, that's worth 21 points. But if I were to draw a 6, and I'm at 12 now, and I decide to hit, and I draw an ace, right? Well, if it was 6 plus 6 plus 11, I definitely have just lost with the 23. But the ace can be worth 11 or 1. and you get to decide what it's worth. And obviously, you want to decide the value that doesn't make you instantly lose. So, so that should be a total of 13. So in other words, so basically, it's a fairly easy way. There's a fairly easy way to score it, which is that you count your 11s as 11, okay? Unless counting them as 11 means that you go over 21. In which case, you would subtract 10 for every single 11 that you have. Okay, which is not that hard to do. So actually fairly simple. If 11 in hand, that's all we care about. Oh, sorry, if 11 is in hand and some hand is greater than 21, then that's our special case. And I'm just going to write pass so that we get back to it. That's all we care about. Otherwise, just simply the value of the hand is just add all the numbers together. That makes sense? Right? So the value of the hand so the value of the hand, normally all you have to do is just add up all the cards you have in your hand. The only exception to that is when you have an 11 or an ace, because an ace can be an 11 or a 1. Okay? So if we have an 11 in the hand, and that currently means we're above 21. Make sense? That probably means we want to treat the hand as that probably means we want to treat the aces as a 1. Okay. So let's see. So let's go ahead and say value a total is equal to sum of hand. Okay, and then what we can do is that we can count. Let's see. I believe there's a list.count method, right? So if I say, for instance, I were to do this, we have 5 L's here. L.count 1. That tells me there's 5 ones in there. Very useful. So what I can say is for blank in range, total. Oh, and by the way, I've never experimented with playing with blackjack like this before, or statistics. But once you get to this point where you're comfortable doing counting and playing with loops, it's not that hard. For blank in range, hand.count 11. In other words, I want to do this for as many times as I have an 11 in there, right? It's possible for me to have more than one ace in my hand. So now, does anybody know? Actually, I've got a question here. So aces are 11s and 1s, but if I have 2 aces, do I have to count them both as 1s? I do? I can have one as a 1 and one be 11? We'll go with that, because that's what I'm currently programming. I just wanted to make sure. The other way was easier. But for blank in range, hand.count 11. So count up the 11s. Total is equal to total minus 10. Why minus 10 if it's an 11? Well, 11 minus 10 is 1, so we're just subtracting. So basically what we're going to do is we're going to go through each ace in the hand and say, does counting this ace as a 1 bring me below 21? If total is below 21, return total. And then at the end, just simply, if somehow we didn't get below, then we got to return the total value of it. So return total. Right? If you somehow have 2 kings and 4 aces somehow, right? Somehow. It's an impossible hand to have, but if you somehow had it, right, this would still work for that. So how do I basically, so the question is, how do I draw cards from my deck then? The answer is I can slice stuff. I can also use an operation called pop, which will get the last card in the deck, and all we have to do is just treat the last card as the first card. Doesn't matter which end we go from. Okay. So we can do slices. We can append to something. If we really didn't care about order, we could do choice, but honestly, we want to keep a consistent choice in this. Also, sometimes you deal with more than one deck. How do you deal with more than one deck? Deck is equal, you just simply call create deck multiple times and concatenate it. Or since creating a deck creates a random deck, you can just simply multiply it by, like, if you need 8 decks, you could multiply it by 8, and then it will have 8 decks there, and then shuffle them up for you. So it's fairly straightforward. So we've got the method of creating a deck, and we've got the method of checking the value of a hand. So let's go ahead and just do our very basic, very basic analysis, which is given an initially empty deck, right? Given an initially empty deck, what is the what are the chances of you get, is the distribution of opening hands, okay? Now there's a couple things that is going to make this a bit trickier than rolling dice, which is that when you're rolling dice, you can get repeats. Like you can roll 6, you can roll another 6, that's not going to impact, you rolling a 6 now does not impact you rolling a 6 in the future. But with decks, that's a bit more tricky because you're drawing cards from a deck and you don't replace that card. So if you draw a 10, or if you draw 2, then there's now only 3 2s, so that reduces the chance of you drawing a 2 from 4 out of 52, because there were 4 cards, there were 4 2s in 52 deck, in a 52 card deck. And that's now the chance of you drawing a 2 for your second card is 3 out of 51, which is vastly different. Well, slightly different. Not vastly, but it's different is the point. So, and also as a result, we should probably simulate, so to make this, so let's go ahead and say def simulate two-player opening hands. And what we're going to do is that we're going to take in a lot of arguments over here, which is that we're going to take in the trials, the number of times I want to simulate it. We're also going to take in, we don't need to take in a deck or anything. We'll create the deck each time. We're going to create a new deck each time. We're going to say from an initially empty deck, from our first turn, the first time we're doing a game, what is the distribution of cards we're going to get? And you have to have 2 players to play blackjack. So we're going to just simulate the dealer and the player. Doesn't matter who the dealer is or whether the dealer gets it first or the player gets it first, right? Because we're counting just simulation. But the number of trials is really all we need. Okay, so players. So what we're going to do is for blank in trials. Trials, not triacs, which sounds like a vicious type of alien in a bad sci-fi movie. Results is equal to dictionary. So what we're going to do is we're going to do this a number of times a trial. Each trial, we are going to create a new deck, which might actually be expensive, so I'm not sure what we'll do. We can just simply say, create a deck. We'll create, but you know what? We'll just create a deck for just out of practice. I wrote the method after all. And then we'll do random dot shuffle to shuffle the deck. Okay? We'll shuffle the deck. And then we need to draw 2 cards. Okay? So, list. Let's see. So let's go ahead and look for list in Python. Brief tour of the standard library. Let's go ahead and see. No, let's just look. Python 3 list documents, because I want to make this as easy as possible for me. And that's always a strategy you should. So we can remove, we can pop. Remove an item in a given position in the list and return it. If no index is specified, it removes and returns the last item in the list. So that's fine. So we'll just pop so we'll just simply use pop. This comes from, why is it called pop? It comes from something called from a stack, which is a different type of data structure. And the only operations you can do on a data structure is you can put items on the top of the stack by pushing items onto a stack and popping off the items on the top of the stack. So to remove it. So you can only push items on top and pop them off the top. Kind of like a stack of pancakes, right? You can't remove the middle of a pancake pile because otherwise you end up with a syrupy mess. Same with dishes. You knock over a bunch of dishes if you try to do anything that's not on the top. So what we're going to do is just simply, so we are going to say player hand is equal to that. Dealer hand is equal to another list. And what we're going to do is say player hand is equal to player hand, and it's gonna be weird because I'm not gonna use a for loop, even though it feels like I should, but it's because we need to alternate it. We could actually use a for loop. We deal everybody 2 cards, so for blank in range 2. So yeah, I'll use a for loop. Player hand is equal to player hand deck dot pop. Dealer hand is equal to dealer hand plus deck dot pop. Okay? And we do that twice. Now, why am I alternating? Because I want to make sure the statistics are right. So I got to simulate it as close to real life as possible, which is that everybody gets 1 card at a time. I don't know if the dealer gets the first card or the player gets the first card. Which card? Who does? Doesn't really matter, because if it was because all I'd have to do is just switch around who the player and the dealer is, and honestly, because we're just simply adding these to our results, it's gonna it's gonna work out. So player score is equal to player hand. Is equal to value player hand. So we've got the player's hand, and then let's get the value of the dealer hand. Convenient that dealer and player are the same number of letters. Makes it look nice and clean. Player score, dealer score, and then we do our typical block to add them to our dictionary, which is, hey, have I seen this score before? If player score not in results, if our player scores are not in results, then guess what? That's the first time I've seen it. So results, player score is equal to 1. Else, this is the second. I've seen it before, so results for that number is equal to that number, or the number of times I've seen that, plus 1. And then I do the exact same thing with the dealer score. Copy paste there and say dealer, Control C on the dealer. And there. And then at the end of this, return results. So the weirdest thing was because I am doing two hands, I might as well calculate the statistics on both and combine them together to see what the distribution of opening hands is. Okay, so, and then return results. So what we can do here is then say, what was this? Simulate two opening players' hands. We're going to do that. Let's see. Yeah, before we do that, what we care about is the percentages. So before I do that, before I return results, I'm going to say for results in, or rather for value in results, right? So what we're doing is we're totaling up the values each hand can get and keeping track of them. For value in results, results value, what we're going to replace results value with is we are going to replace it with results value divided by the number of trials we had to do. Return results. And that just changes it from being a count to a percentage. So simulate the number of opening hands. Results is equal to this. We can print our results, but of course they won't be sorted. But let's go ahead and see what we've done, just simply to see if I made a mistake. For blank in trials. Okay. Range trials. See, that's why we need to test things. Cannot concatenate a list. Oh, right. So here it's saying you can't add a list and an int together. So we pop it off into a list. And then adding this like this will do it. But honestly, there's a better way to do it, which is just simply do player hand dot append. Rather than doing that weird concatenation we're doing. Append just simply means add this value. Bam. Okay. Gotta remember I have the appropriate amount of parentheses. Okay, local value reference before assignment. Def value. Okay, where was that line error? It says error is in line 52. On line 24. 52 called 24. Value player hand. Value reference before. Interesting. So local variable interesting. I don't think it likes me I think it's something weird that Python is. It's because I used the word value when I already have something called value. So I turned it into score. So hopefully this is not an infinite loop. Oh, there we go. So there's our distribution of scores. So let's go ahead and print them out in a nice formatted order. And we've done that so many times, I might as well turn it into a function. Print dictionary print dictionary in order, which will take in a dictionary for key in dictionary dot keys sorted print key dictionary dot dictionary key over here. All right. And then print dictionary in order. Gotta love autocomplete. Not just for, you know, swiping on your phone. Don't call it key. That's not gonna work. Result. But as you can see, it takes a while for this to run because I'm generating a whole lot of random numbers all the time. So next before we finish up, I'm gonna speed it up just slightly by just simply reusing our deck a whole lot. So we can see that basically your chances of getting the worst hand possible are pretty low. Worst hand possible is getting 2 2s. Is getting the worst hand possible is getting 2 2s, I think, because with aces at least you've got something that can be considered an 11. So you've got a 1% chance of getting 2 2s essentially. You've got a 1%. You've got actually almost a 10% chance, on the other hand, of immediately getting a blackjack. So there's a 10% chance, basically, that you win big instantly. It's pretty nice. You can see how people get addicted to that. And a 20% chance of getting a 20. That's a 30% chance right there. Mind you, that's the same percentage chance that the dealer has. It's not just you. Right? So, for our last thing, let's go ahead and we'll go ahead and do the create deck again, but rather what we're going to do is we are going to copy this and just simply do instead we're going to simulate what happens if people both hold. 2 players both hold. Okay? And we're going to just count the number of wins we get. So obviously this is not going to change too much, except we're returning a number here. Okay? Wins is equal to 0. And we generate the decks in the same way, but the statistics we care about is different now. We're assuming that basically people both hold, so there's no decisions that people need to make here, right? Which is that, and so we can simply say if player score is greater than dealer score, it's not greater than or equal to, you have to beat the dealer. Wins plus 1, or wins is equal to wins plus 1. And then return wins. Divide by trials, and that will give me the percentage times the player is going to win outright if both the player and the dealer hold, and the dealer's almost never just going to just hold, right? They are going to play to a strategy, which we can simulate some other time. Maybe I give it to you to simulate yourself as basically what you need to do on Thursday in place of me not being here. But anyway, so let's go ahead and see print simulate 2-player both hold. Simulate that 100,000 times. And you win. So now it's got to simulate it for the player winning 46% of the time. So there's already a built-in advantage that we can see right here by having to beat the dealer, right? Obviously, nobody's going to just hold on what they have, but you have to beat the dealer. You can't just tie him or her. 46, but you know that's a 4% difference right there, or sorry, 3% difference, which means that basically the house is going to make some money, but it's not like as bad as it could be on other games where they even get me started on slots, because then I'm going to compare them unfavorably to voting machines to the detriment of voting machines. All right, so that is my lecture for the day. All right, so again, there is no class on Thursday. And you'll get your practice exam next week with what we're going to go over. In 1 second. I need to stop the recording.
Yeah, I got